let's get into it. Again, today it's sort of a more informal class, just talking about where we can go with the real analysis theory that we've built up, what we might want to study sort of going forward, in future math classes, or just because we're, interested in general. We're going to be building to this picture. As Emily says, it's a very artsy picture. I just think it's the coolest picture, my favorite math picture in any textbook. And so we'll try to justify where this picture is coming from and what it means by the end of class. But yeah, so in order to talk a little bit about where we are going or where we can go with real analysis, it's important to talk about the big takeaway messages from the class. And that sort of gave me pause. I was sitting down Monday afternoon, sometime after our last class, and I was trying to think about what I wanted to talk about in this class. And I was trying to think, like, what really are, in my mind, the big takeaway messages in real analysis. And I think you could spin it in a number of different ways, but I came up with these 3 bullet points. First is we've spent a lot of time working to try to revisit some of these big ideas from calculus, things that we had previously seen but not really understood in any deep or meaningful way. And what we've really seen this semester is that calculus not only has this really rigorous underpinning, like this really rigorous background, but or a really rigorous foundation, but the foundation really depends heavily on the real numbers. There are certain properties about real numbers and about the set of real numbers that really make calculus work in ways that it couldn't work otherwise, right? And so we have talked about this in slightly hand-wavy terms, at different moments throughout the semester. But if we just had a number system that dealt with rational numbers, and if the only things that we had were rational numbers, then calculus as we know it would not work. And a lot of the theory that involve limits and closeness and measuring closeness, and sort of formally rigorously defining derivatives and what have you, a lot of the sort of finer details, I guess, that actually make calculus work would fail. So, number one, there is a lot of sort of more challenging theory in calculus that is not actually taught in Calc 1, and we don't actually get a chance to see it until here in this later math class because we don't have the mathematical sort of technical background or the level of mathematical maturity in a first year class as you do now, in this later math class. Bullet point number 2, the set of real numbers is super challenging to work with, often unintuitive. There are really interesting results that stem from this, such as uncountability, right? Measuring the countability of the rationals versus the uncountability of the reals, and the fact that there's some fundamental difference in size between the two, and that it's an enormous gulf, right, between something that's countably infinite and something that's uncountably infinite, that brings up a lot of unintuitive results. And you can create a lot of like really unintuitive examples or counterexamples in the sets of real numbers. The third bullet point I actually think is probably the most important bullet point, and it's one that we'll think about at a few points throughout the course of the day, and it's that you have to put a lot of thought into how you talk about convergence to nearby objects. So how you consider objects that are in some sense really, really, really close to each other. And we've seen this a number of times throughout the semester, and it really is the first place in Calc 1 where things start to feel a little iffy. So when we talked about limits in Calculus 1, right, and we talk about limits and we draw a picture of a graph with a little hole in it, and we recognize that there's a slight hand waviness in Calc 1 that we really, really make rigorous here in real analysis. And in fact, this challenging language of epsilon delta style arguments really comes from this careful consideration of convergence to nearby objects. So that's, I guess, hugely important in being careful how we precisely talk about something being very, very close to something else. And we've seen this a number of times in this class under different guises, but all sort of carefully dancing around this idea of closeness, and oftentimes being framed or being phrased using some language involving like for every epsilon or something like that, right? So for every small distance, you can say something. So here are some places where we've seen this. I think we first saw it when we talked about the supremum of a bounded set, or the infimum of a bounded set, right? So the least upper bound was the smallest out of all possible upper bounds. So it was the upper bound that was somehow closest to the bounded set S. And we saw that, I believe, like right in day 2 or day 3 of the class. We began talking about supremums and infimums. As we went on, we discussed accumulation points, right? And of course, that had a definition that was like a for all epsilon. The deleted epsilon neighborhood is non-empty. That was our first epsilon argument, right? Our very first for all epsilon kind of definitions. And it was the first place where we really got challenged by our definitions in this really fundamental way. So we had the accumulation point definition. I don't know if I need to write this out, but the sort of like for all epsilon, not even there exists an n, just for all epsilon, the epsilon neighborhood, deleted epsilon neighborhood of a point P had a non-empty intersection with S. Right, so we talked about something that happened for every small little epsilon neighborhood around the point P. And an accumulation point was a point that was sort of really, really, really close, infinitely close in a certain sense to the point S. We also talked about convergence of a sequence to a number, right? So we talked about sequential limits. And that was this idea that a sub n could go to a limit L if and only if for all epsilon there exists a capital N, such that if little n is bigger than big N, the distance from a sub n to L is less than epsilon. So we had that definition, again, sort of for all epsilon, so on all small scales of distance, our sequence will eventually end up in that epsilon neighborhood of L. And then finally, more recently, we talked about the limits of a function, right? So the functional limit, that was maybe the most challenging one. That was for all epsilon, there exists not an n this time, but a delta, right? Such that if we're looking at x values that are close to a point P, right? So within delta distance of P, but not equal to P, toss that in there, so not equal to P, we saw that f of x minus L was less than epsilon. And so that was the sort of more rigorous way to say that the limit as x goes to P of f of x is equal to L. Right, so all of these ideas of getting closer and closer and closer to a given point sort of captured in this more precise mathematical language about saying something meaningful about for any epsilon. Okay, so I think these are some of the most important takeaway messages from the class, or from like the sort of content of real analysis. And that's to say nothing of the tremendous work we did actually building our proof writing ability and our sort of like logically thinking through a proof, trying to figure out how to show something. You know, I don't want to understate that part. That part's also hugely important. But as far as like the subject matter of real analysis, these are some of the most important takeaway messages. And so with that in mind, where can we kind of go from here? Well, I think there's really 3 different directions we could go. One would be just sort of take a deeper dive into the weirdness of the real numbers, right? So the fact that the real numbers form a weird set. Can we say more about that? How weird are they? Number 2, we could sort of tighten up some of the work that we've done so far. So I said here, address some holes in our work. I don't necessarily mean that we have work that is incomplete or incorrect, maybe just not as robust as it could have been. And I'll sort of mention at least one example of that going forward. So we could dive deeper into the real numbers, explore things like the topology of the real numbers, or the measure of the real numbers. Number two, we can address some lack of robustness in some of our results. Number three, we can apply the sort of ideas from analysis, so the big list on the previous page, we can apply those ideas not just to the set of real numbers, but to other sets of perhaps weirder objects and see what sort of conclusions we can draw. And so I'm going to talk through at least one example of each of these, I think. So yeah, one example of each of these. So diving deeper into the weirdness, right? So I want to talk about one of my favorite facts. This is something that I learned when I was an undergrad. I think I learned this when I was a senior undergraduate math major. And I still put it up there as one of the top 5 weirdest facts or most interesting facts or most unintuitive facts that I came across when I was an undergrad. So I feel like I would be sad if I didn't share this with you. So we've talked about open covers in this class. A question we could ask is, suppose we wanted to create an open cover that covered all of the rational numbers, right? So we have our real numbers, we have our rational numbers that sit within the real numbers, and suppose we wanted to cover all of the rational numbers. How big of an open cover would we need? And let's explore that a little bit. So first of all, this is a little ambiguous, because when I use the word big, when I say how big, right? Like, what does that mean? That's not a very precise word. I could cover all of Q with a single open set, right? Just the set R itself. R, the set of all real numbers, is an open set. It's one set, and it covers everything. So that's big, but it's also only one set. So I want to clarify what I mean when I talk about this being a big, when I talk about how big this open cover should be. So what I mean, there we go. Okay, so as a reminder, we have this idea of an open cover where we say that sort of our script F is a set of open sets, right? So it's a collection of these open sets, O sub I, such that I is an element of some indexing set, right? So because I is an element of some indexing set, and then O sub I is our open set. So when I talk about how big this open cover is, I'm going to say, suppose that every O sub I is an open interval, right? Which I can denote as A sub I to B sub I. So that's my open set. It's an open interval. And I'll just say that the size of A sub I to B sub I is the length from one to the other, right? So to be really crystal clear, if I have this, and this is the point A sub 1, and this is the point B sub 1, then the absolute value of B sub 1 minus A sub 1 is just this length right here. So I'm literally just measuring the length of my open interval, and that's the size, quote unquote, of that open interval. All right. And then from there, I will just say that the size of the entire collection, right? So the size of the open cover F is the sum over all i's in the open set of B sub I minus A sub I, right? And so the idea then is here's our real number line. Suppose that we have all of Q here, right? So of course there's infinitely many rational numbers here, right? All these points. And I want to try to cover them all with an open cover, right? So maybe I had A1 to B1, and that has some length. Maybe this is like A2 to B2. And similarly, I'm going to try to cover all my rational numbers with some open cover, stretching off from negative infinity to infinity. And my question is, I can create different open covers to do this. What is the smallest size of an open cover that I can use to accomplish this? Right? And there are some possible choices here. Number one, it must be infinitely large. So it must have infinite size. Maybe it's 2, maybe it's 1, maybe it's 1/2, maybe it's 0. And so this question was posed to me when I was an undergrad. And I won't put anybody in this room on the spot to try to make you answer, but take 30 seconds. No, take 20 seconds and try to just think to yourself, which of these answers do you think makes sense? I'll share what I thought. But yeah, take 20 seconds. I'll get a sip of coffee. All right, for those of you who are joining a minute late, got my, maybe not even late, maybe if you just weren't early, I've got Carrot here hanging out, snoozing through the lecture. Okay, yeah, so let's talk about what we thought here. So I'll tell you what I thought. I thought there is no way it is going to be anything other than number 1, right? It has to be infinitely large because the rational numbers extend from negative infinity to infinity. They, basically fill the number line, right? In the sense that they're everywhere. And if I'm trying to stack these open intervals in a way to cover everything, I'm going to have to cover the entire real line. It's going to have to be infinitely long. And I was completely convinced of that. So I don't know where you landed, but if you landed at number 1, you're in good company, because I was 100% convinced of that. Let's talk about the actual answer. I'm going to make a claim that I can cover all of the rational numbers using a open cover of this kind of described here, with a total size of at least, or let's say a total size of 2. And let's talk about that. So this is going to be the idea. We are going to create, first of all, an index to use. So Q, as we know, is countable. Right? We discussed that early in the semester. I maintain the fact that Q is countable and the fact that R is uncountable as the single most mind-blowing thing that I saw in undergraduate mathematics. Right. What I'm about to tell you, I think, is up there, top five. But the fact that Q is countable, R is uncountable, top 1. Okay, so Q is countable. What that means is I can list it, right? So I can list, I'll say countable / listable. So I can list Q by just creating an infinite list, not G, but let's say sort of Q1, Q2, Q3, Q4, ... right? I can create a list infinitely long, but it contains every single rational number in it. And so I am going to let the numbers 1, 2, 3, ... Let those numbers be my indexing set I, and let's define O sub I as follows. Right, so O sub I, that's the ith element of, or that's the ith open set in my open cover, is going to be the neighborhood. And let me try to get the, it'll be a neighborhood centered at the point Q sub I. And the size of it will be 1 over 2 to the I minus 1, I guess, if we're starting at number 1. It'll be 1 over 2 to the I minus 1. So we have every single rational number in this list right here. And the open cover that I'm creating will be an open cover of a certain size, a neighborhood, right, of a certain size around that point on the list. So for example, O sub 1, right, let's list out a few examples. So O sub 1 would be the neighborhood of 1 over 2 to the 0, that's just 1, right, around Q sub 1. O sub 2 would be the neighborhood of size 1/2 around, I've done this in, I'm so sorry. I meant to say this is going to be the neighborhood, this should just be 2 to the I. I'm sorry. just to make sure that it lines up with what we said on the previous page. So that would be 2 to the I, so that's 1/2. This should be 1/4 around q sub 2. O sub 3 will be n sub 1 over 2 cubed, so that'll be 1/8 around q3, and so on, right? In general, O sub I is going to be n sub 1 over 2 to the I around q sub I, right? And so what we've done here is I'm gonna draw my number line. So there's my number line. I'm gonna mark off, so I have all of the rational numbers, all infinitely many of them, on my list. Let's say this is q sub 1. Let's say this is q sub 2. Maybe this one's q sub 3, and so on, right? And I know that every single rational number is going to get hit by this list, so I'll end up catching them all. Then my O's are defined in such a way that O sub 1 is right here. O sub 1 is going to be, we said, the 1/2 epsilon neighborhood, or the 1/2 neighborhood around Q1. So it's going to be the open set that goes 1/2 units up and 1/2 units down, right? So the total width of this interval is 1, right? If I took this number minus this number, that total width would equal 1. And so the size of O1 is equal to 1. Now 2, right, q sub 2, we're going to create a little epsilon neighborhood around this with epsilon equal 1/4. So that means this distance is 1/4, this distance is 1/4, and so the size of that interval is going to be 1/2, 1/4 plus 1/4. All right, so the size of the first interval was 1, and the size of the second interval was 1/2, and so we should keep a running list. So the total size so far is 1 plus, that one was 1/2, plus the third interval. Maybe you can see where I'm going here, right? The third interval will be around Q3, and it will be of size 1 over 2 cubed. So each radius here will be 1/8. That'll be 1/8. That'll be 1/8. And so the entire width, that entire width, will equal 1/4. And so the total length of all of the intervals we've done so far is 1 plus 1/2 plus 1/4 plus, you can imagine, Q4 will surround Q4 with an interval of size 1/8. Q5 will surround it with an interval of size 1/16, and so on, and so on, and so on. Notice the intervals that we've created already have other rational numbers in it, right? So maybe, you know, q sub 99 is in here, but that's okay. I don't really care. I'll just, again, create O sub 99, which will be a teeny tiny open interval around there. I don't actually care that they overlap, right? Open covers don't care if the same points are covered by multiple open sets. So that's all good. And so we'll end up constructing this open cover whose total size is, well, first of all, the open cover covers every rational number, right? Because if we have a rational number, then it was some number on this list. Maybe it was the 99th number, maybe it was the 3 millionth number, but it's going to be on this list. And so it's guaranteed to be in one of these open sets, right? So this construction of open covers, this will cover the rationals. So call this F. F covers the rationals. And the total size is going to be 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus ... And that is a geometric series. And we know what that sums to. That actually sums exactly to 2, right? And I've been talking about this all day, every day recently with my Calc 2 class, right? We know that this sums to 2, because if you have this total, let's say you have this total length here from 0 to 2. Hopefully you can still see this at the very bottom of the screen, from 0 to 2, right? If you were to go 1 unit and you were to go an additional 1/2 unit, you'd be there. Then you add on an additional half of that, right? That's adding on a 4th. You add on a half of that, you add on an 1/8. And so you keep adding on these individual pieces, each a half of the previous one. In the infinite series, you'll end up summing to 2, right? You'll get all the way there in the infinite series. And so what we have shown is that not only does this open cover the rationals, but its total size is equal to 2. We can cover this infinite set, the infinite set of rational numbers, with an open cover whose size is equal to 2. Crazy. I'm going to pause for a second. Any questions about the argument that we've constructed, or comments, or concerns, or anything?
If we end up starting the set instead of 1/2i, if we end up starting the set 1/2 to the 2i, can we reduce the distance covered? So it would be what? 1/2, so it'd be 1.
Ooh, okay. So Emily, you have preempted the comment I was going to make. So I was going to throw this question out, and I think you've seen where I was going there. So ignore the fact that this looks terrible and all the writing is on top of each other. Looking back here, notice that I had said here I've covered it with an open cover of size 2. The question we asked is, what is the smallest size we can use to accomplish this? Does that mean the answer is 2? And Emily, you're absolutely right. That's no. The answer is no. What if instead of using size 1 for my starting point, I had used size 1/2. So I had started with size 1/2 there, right? Meaning I went out a 4th in each direction. So the total size was a 1/2. And similarly, I cut each of these down in half, right? So every single one of these is half the size. Well, the construction is still the same, right? Every step of the way is still the same. F continues to cover the rationals, but under this new setup, this would have been 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus ... It would have been half of the original open cover. And so its total size would not be 2, but it would be 1. So 2 is not the smallest. Turns out we can do it with size 1. Does that mean size 1 is the smallest? No. So it turns out there is no reason why I had to make the first interval any given size. In fact, I could have made the first interval a size epsilon, right? So instead of making the first interval size 1 or the first interval size 1/2, if I had made that first interval size epsilon, and I had made this second interval size epsilon over 2, and this one size epsilon over 4, epsilon over 8, epsilon over 16, and so on and so on, I would have just changed all of these. I would have thrown an extra epsilon everywhere. I guess I would have had to add a +1 to make this line up. So 2 to the n plus 1 in the denominator. But I would have ended up with a total size that is equal to epsilon over 2 plus epsilon over 4 plus epsilon over 8 plus epsilon over 16 plus epsilon over 32 plus ... I can cover all of the rational numbers, which we think of as being pervasive everywhere. I could have covered all of them with a total covering of size epsilon for any epsilon. And so it turns out, what is the smallest size of an open cover? Well, there is no smallest size of an open cover. For any epsilon, any small number epsilon, I can find a way to cover all the rational numbers with an open cover of total size epsilon or less. And so it turns out that the real answer to the previous question is more like 0, right? That we can actually cover this with open covers that get arbitrarily small in size. So it is another sign of how tiny, how incredibly small the rational numbers are in this incredible sea of real numbers. And this is sort of an entry point to what is called measure theory, which is a class that one could go on to look at after real analysis, right? What we've just shown is that Q has something called measure 0. And more generally, we can define the measure of a set as the infimum of the sizes of these open covers. Notice the footnote. This is actually not totally true. The technical definition is more technical, but for the last day of real analysis, it's fine. It's close enough. And so what we have shown is that Q has measure 0. And that same argument says that every finite set or every countably infinite set has measure 0. At the same time, any closed interval of real numbers has measure equal to the size of the interval. So the closed interval from 0 to 1 has measure 1, which means that the closed interval from 0 to 1 is somehow thicker than the set of all rational numbers together. There are a few other examples that we've seen. The Cantor set turns out has measure 0. The set of all real numbers has infinite measure. And in general, measure theory is important when it comes to looking at sort of like more complicated applications of real numbers. There's a lot we can do here, which of course we won't do today, but this would be an appropriate sort of independent study or selected topics or first year graduate school course if you were interested in mathematics sort of above and beyond real numbers. There's, like I said, a lot to go into. Things we won't get to talk about today include questions like, is every set of real numbers measurable? Well, the real numbers are really weird and you can construct really weird examples. So surprisingly, or maybe not surprisingly, the answer is no. You can find some sets that are not measurable using the more technical real definition of measurability. So measure theory is a great place that you can go from real analysis. Okay, that was bullet point number 1, getting into the weirdness of the real numbers. Bullet point 2 is addressing some of the holes, quote unquote, that we haven't gotten a chance to talk about, or some holes in our real analysis work so far. So I want to talk a little bit about the integral, which we introduced last class, right? So the Riemann/Darboux integral, I guess specifically the Darboux integral, is fantastic, and it's a great point to get to in real analysis, but in a certain sense, it's not very powerful. And what I mean by that is that there are a lot of functions that are not Darboux integrable. For example, functions with lots and lots and lots of discontinuities are not Darboux integrable in a certain sense, right? So we have to define what we mean when we talk about many discontinuities. So for example, the function that we've seen from time to time, the function sometimes called the Dirichlet function, that is defined to have a height of 1 on every rational number and 0 on every irrational number, this is not Darboux integrable. And I want to make a loose argument for why that is. So first of all, as a reminder, this function f of x, I'll draw it here in purple, it's going to be a height of 1 on every rational number. And of course, there are infinitely many of those. Let's say between 0 and 1. And between 0 and 1 on all the irrational numbers, it has a height of 0. Right? So it has all of those points up there at 1 and all those points down there at 0. And if we try to construct a Darboux integral using our theory from Monday, we would have to try to look at partitions, construct upper sums and lower sums of those partitions, and then look at the upper integral, which was the infimum of all of those upper sums, and the lower integral, which was the supremum of all of those lower sums. And I don't want to spend too much time rehashing it, but I will point out that if I construct a partition, so here's my nice arbitrary partition, we'll call that, partition P, that if I have a partition P, my upper sum for the function f with the partition P is what I'll get when I multiply the lengths of these intervals times the maximum height / the supremum height, which is always going to be 1. So I'll end up adding up all of these little intervals, or all these little areas of height 1, and I'll end up getting the area of this entire box, right, whose total width is 1, whose height is 1, and so we'll end up getting that the upper sum is equal to 1, no matter what my partition was, just because there are so many points up here at a height of 1. Similarly, my lower sum, right, that's going to be these intervals, the lengths of these intervals times the infimum value, the infimum function value. And so that would be all of these points down here, right, at height 0. So we would end up adding up a bunch of zeros multiplied together, and the lower sum of f with partition P would be 0. And so this is true for any partition P. And as a result, the upper integral is always equal to 1. The lower integral is always equal to 0. I should have said the upper integral of f, the lower integral of f. And because those two numbers are not equal to each other, right, because they're not equal to each other, this function is not Darboux integrable. And so we do not converge to an actual integral. And so this is a problem, potentially, right? This is a problem with the Darboux integral. It's that here is a bounded function f, but it is not Darboux integrable. And functions with lots and lots of discontinuities like this turn out to not be Darboux integrable. So how do we address this? Well, we can address this with a more advanced definition of the integral. And usually what we do in mathematics is we introduce something called the Lebesgue integral. So more powerful than the Riemann integral, more powerful than the Darboux integral. The Lebesgue integral does something really interesting. Instead of breaking up a partition in the domain, right, and then measuring the heights in the domain, this is what the Darboux integral did. This is what the Riemann integral from Calc 1 did. Instead of breaking up a partition in the domain, the Lebesgue integral breaks things up along the codomain. So it breaks things up into small pieces along the codomain. And what it does is it looks to see, let's say it takes some little interval around the height 1. It looks to see the set of everything that maps to that height. So in other words, it looks at all of these x values down here that map to the height of 1 or near 1. Right? And that, using our language from real analysis, would be the pre-image of 1, right? So the pre-image of the height 1, maybe should put some brackets in here. Anyway, the pre-image of the height 1, it looks at that set in the domain, and then it takes the measure of that set. So using this new idea of measure theory, it takes the measure of that set and multiplies it by 1. So it's still a measurement of width times height. It's just done a little differently, where the height is what is first looked at, and then the width turns out to be the measure of the underlying set that maps to that height. And it turns out that the Lebesgue integral can handle an expression like this because, well, I should say it gives us an answer, and an answer that kind of makes sense. What we have seen here is that our function is equal to a height of 1 at all of these rational numbers, but all of these rational numbers taken together, we claimed, have measure 0. So the Lebesgue integral says that all of this height that's coming from up here doesn't actually contribute to the integral. It would end up being that height of 1 times the measure of the base, and the base had measure 0. So all of that is contributing essentially 0. And so the Lebesgue integral would compute a answer for this function f, and under the Lebesgue integral, right, the integral of the function f would equal 0. So what makes the Lebesgue integral, besides being sort of unintuitive and a little wonky, what makes the Lebesgue integral more powerful? Well, the Lebesgue integral agrees with the Darboux integral and the Riemann integral on every function that is Riemann integrable or Darboux integrable. So every function that's regularly integrable, the Lebesgue integral gives us the right answer. And oftentimes, if a function is not Riemann or Darboux integrable, the Lebesgue integral gives us an answer that we can make sense of. So it's a more powerful version of the integral. And oftentimes, in studying something like measure theory, you would go on to examine the Lebesgue integral and its nuances. So a cool sort of, again, sort of like advanced class, either a measure theory class or a real analysis 2 style class, or a first year graduate school class, something like that would be a place where we could examine these kinds of more complicated functions, or more complicated integrals, I guess. Okay, that was bullet point number 2, sort of tightening up or making our theory stronger by introducing some more advanced strategies for accomplishing these things like taking integrals. The final bullet point that I wanted to talk about, it's sort of the most fun bullet point in my opinion, is talking about these analysis strategies that we've begun looking at, and we've looked at them primarily in terms of real numbers, and seeing how they can apply to other weirder spaces of objects, right? And so there are some natural places that we can go. A classic one, and one that is often a class that's offered at the undergraduate level, Dr. Richards teaches this class reasonably often, maybe every other year, is complex analysis. It's not quite as wonky or as technical. In a certain sense, it uses less epsilon delta style arguments, but it is using these arguments from real analysis applied to the set of complex numbers, and that can give us complex analysis. We can also talk about looking at spaces of functions defined on a common domain, right? So we can apply, or we can study these spaces of functions. We can apply theory from real analysis to them, and that gives us sort of an inroad into a subject called functional analysis. And then something that's near and dear to my heart, if you look at geometric spaces, like spaces of objects or sets of surfaces embedded in some ambient space, that can lead to something like geometric analysis, which again is my personal favorite. And so let's talk about what this sort of looks like, applying real analysis strategies to these weirder, more abstract spaces. There are a couple motivating questions, so questions that we looked at in various guises a lot in real analysis. And these are the questions that we might carry forward into these new settings. One of the most important questions actually is this first one. Can we take a sequence of objects, where again, objects could be functions, they could be geometric surfaces, they could be whatever, but can we take a sequence of objects, i.e. sort of an infinite list of objects, and discuss whether this sequence converges to an object in any meaningful sense. In order to talk about convergence, we often have to talk about how things are measured in terms of distance, right? So if we want to talk about convergence, we want to talk about our objects getting closer and closer to some limit object. And so we have to discuss how do we measure distances in these abstract spaces, right? Maybe, I don't know, maybe the way that we, well, actually I do know, the way that we measure distance in the real numbers, right, is that the distance between 2 points x and y, you could say the distance between 2 points x and y in the real numbers was just given by the absolute value of x minus y. And we might ask the question, how do we measure distance in these more abstract spaces? So maybe the distance between two functions f and g defined on a common domain, right? It's like so from a to b. Maybe the distance between them is something like the integral from a to b of one minus the other, right? Maybe that's how we choose to define distance. And that could give us a sense, right? If the two objects are the same, if f and g are the same function, then this integral would become 0, and we would say that they're distance 0 from each other. So maybe that's how we define distance. Or maybe we do something else, right? Like maybe we define the distance by taking the distance between the two and squaring it, right? Maybe that's how we define distance. And why would we define distance one way over the other? And what are the advantages of doing that? So that is a question that we can ask, right? And that typically involves the study of these objects called metric spaces, where metric is meant to measure a distance, right? A metric is a measure of distance. So we might ask ourselves, how do we measure the distance between two objects in our set? In other words, how can we define a metric space, or how can we define a metric on this abstract space and turn it into something called a metric space? And what implications are there once we have a metric for sequences of objects converging to some limit object? Finally, always an important question, suppose that a certain property is present in each of the objects in our sequence. So we still have a sequence of objects converging to some limit object. And suppose each of these objects have a certain property. Is that property definitely present in the limiting object, right? Or in that limit object? So an example of this that we saw in real analysis was the order limit theorem, right? Which said that if you had a sequence of numbers, a sub n, and a sub n converged to some number a, and if all of those values a sub n was, let's say, non-negative, right? If all of our a sub n's were eventually, or let's say they all were, greater than or equal to 0, would that property hold true for the limit? Would a have to be greater than or equal to 0? And it turned out the answer was yes. If our values were non-negative, then a would have to be non-negative as well. But if we change that non-negativity, if we tried to strengthen it and say strictly positive, if we had a sequence of positive numbers, would that have to converge to a number that's positive? No, not necessarily. We can have a sequence, you know, like 1 over n, that's all positive, but it's converging to something that is actually 0. So we could have something positive converging to something that is positive or something that is 0. So non-negativity was, I should say non-negativity was a property that carried through a sequence, while strict positivity was not. And we can ask ourselves in these more abstract spaces, what properties am I interested in? And is a property that's present in a sequence of objects, can that carry through into the limiting object? And that's often a really, really interesting question. So it turns out, surprise, surprise, one example of this is something that I've actually embedded in your final exam, in your take-home final exam. One example is about sequences of functions. We can talk about functions, yeah, right? We can talk about functions that are defined on the set 0 to 1. Right? We can talk about functions that are defined on the set 0 to 1. And we can talk about a sequence of functions converging to a limit function, right? So these f sub n's converging to f. And we can ask a question, does a certain property, like continuity, carry through to the limit, right? If all of our individual functions are continuous, does our limit function have to be continuous? And it turns out the answer is that it depends on our definition of convergence in this new setting. If our definition of convergence is pointwise convergence, then continuity does not hold true, right? We can have a sequence of continuous functions converging pointwise to a discontinuous function. And one of the questions asks you to explicitly walk through and see that it converges to this discontinuous function, right? That was the set of functions of the form x sub n converging to this function that is 0 everywhere except right at the number 1 where it jumps up to 1, right? So there's a discontinuity there. And you're asked to rigorously show that that's the case. However, if we introduce this new kind of convergence, right, this so-called uniform convergence, then the answer is yes. If our sequence is continuous and our convergence type is uniform convergence, then continuity is preserved as we go from the sequence of functions to the limit function. And that was, again, one of the questions that you're asked to look at on your final, that the uniform convergence of continuous functions yields a continuous function. Yeah, so an example of this sort of in action, where you can see it's just a tiny little half step above what we've done in our class. In the fact that we're actually doing it in the class just on the final. As a fun side note, I just wanted to mention this. Sequences of functions are things you've seen elsewhere in mathematics, though we maybe didn't use this language when we were talking about them. Does anybody know what this picture is? What is this a picture of? It's been maybe a couple years since you've seen it, but what is this picture?
Y equals x squared, y equals x cubed, y equals x to the 4th, and y equals x to the 5th, I think.
Aha, so some of those are right. Not all of them.
Okay, it's only the odd functions.
It's only going to be the odd ones. Yeah, so this one here, like this is y equals x. This is an odd one. It's not quite y equals x cubed. It's actually the more interesting, for today's lesson, more interesting function, y equals x minus x cubed over 6, right? Or I could suggestively write that as x minus x cubed over 3 factorial. Which one is next? This one, right? This is y equals x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. And then the last one, it's going to be all of that again minus an x to the 7th over 7 factorial, right? So
talk about Taylor series.
Yeah, so it turns out these are our good old friends, the Taylor series, or I should say these are the Taylor polynomials, right? We have a 1st degree, a 3rd degree, a 5th degree, and what I'm just going to finish writing right now is a, oh my goodness, I can't write and talk at the same time. What we're finishing here is a 7th degree Taylor polynomial. Just finish writing this quickly. It doesn't really matter because you've gotten the idea here. Yeah, these are all Taylor polynomials that are describing the function that's here in black. This is the function, our good old friend, f of x equals sine of x. And each of these are the Taylor polynomial expansions, the 1st, 3rd, 5th, and 7th order Taylor polynomial expansion for the sine function. So what we saw in Calc 2, right, and I'm teaching Calc 2 right now, so this is all like front and center in my brain. What we saw in Calc 2 is that Taylor polynomials converged to, if we think of them as a sequence of functions, they converge to the Taylor series, which is a series representation of this underlying function. So we can talk about a sequence of functions, namely these different Taylor polynomials, converging to the sine function using potentially either pointwise convergence or uniform convergence, depending on how we spin it or depending on how we sell it, or how we set it up, I should say. So yeah, this is really important sort of mathematical theory here that we saw in Calc 2, but we're really only beginning to understand at a deeper level here near the end of real analysis. And so this example, Emily, you said it, this example is an example of Taylor polynomials and Taylor series. And we've also got, and I don't have a picture of it, unfortunately, but we have other kinds of function series as well, right? So we have, for example, things like Fourier series. And those of you who are either more physics inclined or acoustically inclined, or maybe you took that special topics class with Dr. F maybe 2 years ago, maybe just last year, maybe 2 years ago, might have talked about Fourier series and how they are built up in a similar manner to Taylor series. So different ways that we can construct sequences of functions, right? Just in the case of these series, they're sequences of polynomial partial sums that converge to an underlying function. And in those kind of studies, understanding the rate at which they converge, being able to find the appropriate delta to go with your epsilon, and being able to know what properties of the series carry through are all really, really, really important. So yeah, just an example of how we can use this real analysis theory to both address this question from Calc 2, but we didn't really understand it in Calc 2, or alternatively, how we can use these ideas from real analysis to address really important applied math problems, right? And Taylor series and especially Fourier series are used in a wide array of applications sort of in the real world. Cool. So much fun. One thing that I wanna sort of talk about here in the closing bit of time is the surprising importance of compactness. So this really sort of, in many ways, I think compactness is one of the most challenging things that we talk about all semester, right? The idea that every open cover admits a finite subcover is really, really hard to wrap your head around, especially at first, right? If it's the first time you've ever seen it. I still think it's really challenging. But compactness turns out to be a really important thing as you begin to move away from the real numbers and into these more abstract spaces. And that's because compactness is a certain measure of smallness, for lack of a better word, right? Or compactness, but I don't want to use the same word again. Compactness is a measurement of smallness in an abstract set that can be useful. And it applies directly to these questions we're beginning to think about, these questions of sequences, and do these sequences converge to a limit? So one thing that we saw, I think beginning of last week, one thing that we saw was this idea of sequential compactness, right? And when we talked about sequential compactness, as a reminder, we saw that sequential compactness meant, right? Let's just sort of write this out. Sequential compactness meant the following. We said a set or an abstract space, S, we said S is sequentially compact. I butchered the grammar here. Let's say S has sequential compactness if, and only if, every sequence in S has a subsequence that converges to a point in S, right? Or maybe because we're talking about these more abstract spaces, maybe I shouldn't say a point, maybe I should say to an object. So every sequence of objects in S has a subsequence that converges to an object in S, right? That was what was meant by sequential compactness. We saw in the day when we discussed this, we saw that sequential compactness turned out to be equivalent to original compactness, right? And in our class, we said that compactness was two things, right? The original definition was every open cover has a finite subcover. So that was true, or that was the definition of compactness. We saw through a lot of your work, I should say, one of like the last really heavy days of your group work, right? One of those great days near the end. We were able to show through a series of your results that this is equivalent to the so-called Heine-Borel theorem, which said that this is true if and only if the set is closed and bounded. Right, so every open cover has a finite subcover. We saw that was true if and only if the set was closed and bounded. And then what we've just seen is that that was true if and only if the set was sequentially compact. Right, whose definition is just written below, that every sequence has a subsequence that converges to an object in the set. So why is this important? Well, one of the questions that we're interested in is the question of, do sequences of objects converge to some limit object? And sequential compactness guarantees that our sequence might not converge, but some subsequence of it does converge. So if we're working with an abstract object or an abstract space of objects where it's hard to think about what it looks like, if we know that the space is compact, then we know that it's sequentially compact, which means if we take some sequence of objects, we're guaranteed that a convergent subsequence exists. And so we can guarantee at least that with some subsequence, it converges to some limiting object. And that's huge in some of these really abstract situations where it's hard to even think through what these objects look like or what the possibilities are. That can be really helpful. So sequential compactness, which is equivalent to regular compactness, turns out to be really important. As a side note, once we are no longer working in the set of real numbers, compactness does not necessarily equal closed and bounded. So this result here, right, the Heine-Borel theorem only works in R. So as we transition out of real analysis and into, say, functional analysis or geometric analysis, we have to be a little suspect of this, unfortunately. So we have to keep working with open covers and finite subcovers and sequential compactness. So that's a shame. That's a drag. That is too bad. But still, we can see the importance of compactness and sequential compactness here. And that brings us to one of my favorite problems, right? Again, this is the sort of stuff that I love to think about. The soap bubble problem. And here we're starting to circle back around to that first picture. Suppose that we take a smooth surface embedded in three-dimensional space, right? So a surface is this two-dimensional object. It's sitting inside of three-dimensional space, and it has a boundary given by a closed curve, right? So in this picture, we have the closed curve is just this circle. My goodness, just this circle around here, right? And it sort of extends beyond the back. And then the surface itself is like this little hill that is coming up here, right? But it's this two-dimensional surface that has this curve, this circle as a boundary. If we think back to Calculus 3 theory tells us that we can measure the surface area of such a surface, right, by setting up an appropriate parameterization. I should say those of you who are in my geometry class also saw things like this, right? You can set up an appropriate parameterization of the surface, like an f of s comma t. My goodness, I'm going to forget all of this. And then the area of the surface, f of st, is something like this. It would be a double integral over your s boundaries and over your t boundaries. You would have to take t sub s, you'd have to take t sub t, you'd have to cross them, and you'd have to take that, let's just say ds dt back there. So you'd have to cross them, you'd have to take the norm, and you'd have to integrate that over a double integral. We saw that in Calc 3. And then in geometry, we actually saw how this was an example of integrating, right? In geometry, those of you who are in my geometry class, you saw how this was actually an example of integrating up the determinant of our first fundamental form, right? The Gij. So we could integrate up the determinant of that first fundamental form and get the surface area. So if we have a closed curve that bounds a surface, we can measure the surface area of that surface. And that should be some finite number, right? So this surface area is some finite number A. Now, let's take a step back and not look at this particular surface, but imagine this abstract set or this abstract space that is the set of all smooth surfaces with the same boundary curve, right? So every object that I'm looking at has this circle as its boundary curve, and I can take all of these different surfaces that sort of emerge from there, and I can measure each of their areas, A, right? Can we find one with minimal surface area? So out of all of these surfaces, can we construct one that has minimal surface area? This is called the soap bubble problem, by the way, because if I took a wire frame with that boundary curve and dipped it into soap film and pulled it out, the resulting soap film that would cling to the wire frame, that would be theoretically the surface with minimal surface area, right? So these type of objects are recognized or are realized in the physical world using soap film and using bubbles. So first of all, we expect that the answer will be a flat disk, right? This is sort of our intuition or our gut feeling. So the flat disk should be an answer to this problem. And if this is the unit circle, right? So suppose that this has radius 1, then the flat disk has surface area pi times the radius squared. So this would have area pi. So we expect that pi should be the minimal surface area, and that the actual surface that achieves this is the flat disk. Right? And that's a very, very, very good assumption. It turns out that's the correct assumption, and it turns out to be true, but it's very, very hard to explicitly show that. So here is a real analysis approach that we could make, right? A real analysis approach would be to recognize that the areas are bounded below, right? Every single surface has a measurable surface area, and the set of all surface areas, if we look at all of those different real numbers, they're bounded below by 0. You can't have less than 0 surface area. So they're definitely bounded below by 0. And therefore, some infimum value, some greatest lower bound must exist out of all of the areas A, right? That's true by real analysis, because these are just real numbers that we're talking about. They're bounded below, and so a least upper bound must exist. So now using these new ideas, let's do the following. I should say, by the way, that we hope our alpha value is equal to pi. That's what we're hoping for. we can then construct a sequence of surfaces in this abstract space whose surface area is decreasing towards the infimum. So we figure out what this infimum seems to be. We think it might be pi. We can construct a sequence of surfaces whose surface area is decreasing towards this infimum. And if we're lucky, and we can show that our abstract space is compact in some meaningful sense, we can extract a convergent subsequence. And then if surface area is a quantity that is preserved through limiting process, then this convergent subsequence would necessarily converge to a limit surface that has area equal to the infimum. And so that's our strategy. And this brings us to a great, this brings us to our picture basically, because it turns out, oh darn, the set of surfaces is not compact. What I mean by that is that we can create a sequence of surfaces that don't have a convergent subsequence. And here is an example of that. What we see here is a sequence of surfaces. Imagine this upper left surface. Let's say this is surface 1. Let's say this is surface 2, surface 3, and surface 4. So these are the first 4 surfaces in a sequence of surfaces. And notice these are designed so that the surface area is decreasing every single time. So this is a sequence of surfaces that is moving towards the infimum. They all become a surface with surface area pi plus a teeny tiny bit. And that teeny tiny bit is decreasing. But the space of surfaces is not compact with respect to this surface area measurement. And what can happen is that you can create surfaces of arbitrarily small surface area with an arbitrarily complex shape to them. And the reason is because surface area, right, you can construct these little tendrils, and if you make the tendrils skinny enough, then the surface area will be very, very, very small. So I can create this sequence where my tendrils get skinnier and skinnier and skinnier, the surface area gets smaller and smaller and smaller, and yet the tendrils branch out in weirder and wilder ways, as we see in this final picture. And so this sequence does not actually converge to the solution we were hoping for. And this is an important example of why this sort of question of compactness is so valuable. Oh my goodness. And so with that, we're actually out of time, which is great because we actually got to the end of the lesson. But yeah, I'm a little sad that things are ending. Yeah, you can notice a lot of fun little fun little hidden gems in this picture. You see the tiny bird. You see this looks like it's holding a pencil. I like to think that much like an Escher drawing, this last surface is sort of illustrating itself. You see an example of the trefoil knot hidden in here. So there's a lot of fun little things here. I really love it. Such a fun picture. Anyway, yeah, thank you all so much for listening to me today, and more broadly for being such an absolutely wonderful class. It's been a lot of fun to work with you all, both in the room together, and then when we had to transition to this online learning, you all really took to the Google document, sort of collaborative work in a really wonderful way. And I didn't quite know what to expect when I suggested it. And I was really, really happy with how you all, were willing to engage with that and jump into it. So you are a really great, fantastic group of students, and I'm absolutely going to miss you all. So yeah, so take care. Have an absolutely wonderful rest of your day, rest of your week. Reach out to me if you have questions about the final, and I'll be around, happy to chat about those. Also, let me know if you want to chat sort of immediately after this class about the credit, no credit situation. I'm very happy to talk to you about that. Take care out there, sort of a weird world right now. So take care of yourselves. Have a wonderful summer. If you're graduating, congratulations. Come back and visit. Come back for the graduation so we can congratulate you in person. If you're not graduating, come back in the fall. We'll keep studying fun math stuff together. Yeah, thanks so much, everybody. Take care and have a great a great rest of your day.
Thank you, Dr. Ross. Bye.
Bye.
Thanks, Joe. Thanks, Jesse. Take care, everyone.